This is a space-time diagram, and to understand it, let's get into the details. Let's start with a single point in space. We'll call this event A. This point can experience time as it moves forward, and it can also move through space. This is what we call a space-time diagram, a map of every event through space and time laid out in one picture. Let's finish building this plane by adding the negative components to both the axes. Everything above the horizontal axis is the future, where we're heading, and everything below is the past, where we've been. To the right, we'll call positive x, and to the left, we'll call negative x. These are just arbitrary conventions, but they're the ones we're going to stick with for the rest of this series. Now, in principle, we could add more spatial dimensions here, but for now, we're going to stick with the simple two-dimensional case with a time and an x-axis. Now that we have our diagrams, let's talk about what happens when an object actually moves through it. This path, the trace that an object leaves as it travels through space and time, is known as a world line. Let's build up our intuition with a few simple cases. First, the simplest case, a stationary object. It has zero velocity. It just sits in space, not moving through space at all. It only moves through time, so our diagram will look like this. A straight vertical line going upwards. The object does not move side to side, only up. So, if a vertical line means not moving through space, what would a horizontal line mean? It would mean that the object exists at every single spatial point, all at the same time. Since that is physically not possible, a horizontal line cannot occur on a space-time diagram. But what if the object appears and then disappears? This is shown as a single point on our graph, which, as we said earlier, is exactly what you call an event. Now for constant velocity, our object moving steadily through space traces out a straight diagonal line. If we wanted to make a negative velocity line, we'd just have to flip our line across the t-axis. By convention, we draw those lines passing through the origin so that we can compare the different velocities by comparing their slopes. So what happens if you tilt the line? Let's say the line is a little steeper than the ones we drew previously, or what if a little shallower? As you can see right here, contrary to what we're used to in mathematics, a steeper line actually means a slower object in space-time diagrams, because it travels through time much faster than it travels through space. And a shallow line means that it's a faster object, as we can see right here in these representations of the blue spheres. Now, you might have noticed that every line we've drawn so far in the graph has been below 45 degrees. That is on purpose because you can go further down, a little shallower, and you get to 45 degrees. This is where the assumption we made at the beginning of the video comes in, that the speed of light, c, equals 1. Because now, the time the light takes to travel, let's say 1 light meter in 1 light second, or 2 light meters in 2 light seconds, is going to be equal. So right between our t and space axes, we have the light line, the world line of light itself. Now, let's add a second spatial dimension so we can really see what's happening here on a more intuitive scale. If we sweep our light line around the new axes, we get a cone. This is known as the light cone, the surface formed by every possible light line radiating out from an event. Since every physical possible velocity is less than the speed of light, every possible world line has to be contained inside of this cone. Same goes for the past as well. Every light that has ever reached an event has traveled inside the light cone. So what would it mean for our angle to be greater than 45 degrees? Most of you might already know that there is nothing that travels faster than light. Therefore, it's not possible. Remember our future and past regions from earlier? Now that we have our light cone in place, we can be more precise. The future of an event isn't just everything above it, it is everything inside the future half of the light cone, because this is as far as light can go. You can also think of this as the fact that you need light to see or observe anything, so it is impossible for us to observe anything that cannot be reached by light. So, what about everything outside the light cone? Everything outside the light cone is known as elsewhere. And as the name suggests, it's everything elsewhere. From the event that you are at, you are physically incapable of observing, reaching, or being affected by anything that is in that region. Light itself cannot make it there in time. So let's put a name to these kinds of lines in our diagram since we will be using these throughout the video. The line sitting exactly at 45 degrees is a light line. Therefore, any scalar multiple of this would be considered light-like. Let's make this concrete with some examples. Say there are two observers out in space, completely unaware of each other. One wants to send the other one signal. The fastest possible way to do so is by sending a light signal. Here is a graphical representation. Trace the signal's path and you get a light line connecting the events. Next, we can have a line steeper than 45 degrees. Now remember, steeper means slower. A velocity slower than the speed of light itself. This is known as time-like, the world line of anything with mass. This time, let's say our observers don't care that much about communicating as fast as possible. So one of them simply throws a ball at the other, traveling at a percentage of the speed of light. Since anything with mass moves slower than light, this path is time-like, a line steeper than 45 degrees. You can throw the object, but it will always arrive later than that light would. You can see this in the graphical representation as well. This line takes much longer and is higher up on the t-axis by the time it meets the observer number 2. Now let's talk about a line shallower than 45 degrees. Shallower means the velocity exceeding the speed of light, which would require velocity greater than c. That is known as space-like. Nothing physical can ever actually travel this fast, but it is a useful category for describing the relationship between two events. And we'll see that in a moment. So if you try to send a message along a space-like path, shallower than 45 degrees, just like earlier, picture turning on a flashlight aimed towards a distant observer at a specific moment. Given how far apart you are, there is a stretch of time during which it is physically impossible for the light to travel that fast. The observer, too, will have no idea that you emitted a light or anything until light has a time to actually travel to them. If you look here, the time a space-like line would take for a message to arrive is much earlier than light can actually reach them. Now here we have an observer and their light cone. These lines are their inertial frames. These are a coordinate system that belongs to an object moving at a constant velocity. As you can see, there is a moment of time where two observers' light cones overlap. This area is their shared future, and another, their elsewhere. In the shared future, they can influence each other. You can move these objects around wherever you want, but there will always be an elsewhere present. No matter how you arrange the two observers in our plane. There is a shared region, where they both can eventually affect each other, and a region that always permanently out of reach for each of them. Unless, of course, they're standing on top of each other, in which case they'd simply be the same object. Let's go back to the two spheres from the beginning of the video. A collision that sends them flying apart traces out their world lines, opposite in direction. So far, we've been watching both of them from the outside. But what if we followed one of them along? Let's shift everything into the blue sphere's perspective. Let's pretend that we ourselves are moving along with the blue spheres. As you can see, instead of the sphere moving, now it seems as if the green sphere and the grid itself are moving in the opposite direction. So how would we represent this on our Minkowski/spacetime diagram? Each observer's world line is by definition parallel to their own time axis, because that is the direction they're moving through time. Let's label this tilt from the t-axis alpha. To build the matching space axis for this new frame, we tilt by the same angle alpha, but mirrored on the other side from the horizontal axis. The result is a pair of axes that are at, quote, right angles to each other, even though neither of them looks horizontal or vertical to us anymore. This relationship is known as orthogonality. You might have heard this word being synonymous to perpendicularity, but being orthogonal in space-time means that they sit at the same angular distance from the light line. One is tilted towards the time side and the other on the space side. So one clarification worth making explicit in this series is that we're using the t and the x-axes to draw these angles, but they have the same geometric meaning if we were to draw them from the light axis instead. Okay, Now let's morph the whole diagram so that the new tilted pair of axes becomes our main frame, the one we treat at rest. Our new graph now shows the world lines in our new reference frame perfectly. Now let's look at this from the perspective of the green sphere. Once again, we do the same thing. It looks like the grid and the blue sphere are moving in the exact opposite direction. How do we show that in our diagram? Once again, using the orthogonal axes that we came up with earlier, we stretch and compress these axes until the desired axes look like a 90-degree. These vectors follow exactly what the animation shows right here as well. Now let's put a grid behind this so we can really see what is happening to every single point in space. As you can see right here, the stretching and compressing is known as a Lorentz transform, the transform that takes spacetime diagrams from one inertial frame to another. If you have taken linear algebra, you might recognize this as a change of basis. That is really what is happening whenever you are shifting from one point of view to another. Let's go ahead and add our light lines onto the diagram. What do you notice? The vectors themselves do not change position. They're simply being scaled up or down. Once again, some of you might recognize this as eigenvectors. This essentially means that no matter what inertial frame you're transforming into, the light lines never move. They stay exactly the same. And that is because the speed of light is constant in every inertial frame. This is not a rule that we are coming up with. It has actually been proven that light has a constant velocity, irrespective of the frame that you're viewing it from. Now let's look at the specific point right here on the time axis. Watch what happens to the point as we transform it through every possible inertial frame case. It traces out a hyperbola, always sitting in the same way relative to the light line. This is interesting because let's remove these grids for a second. As you may notice, both the light lines and the hyperbolas don't change, no matter what inertial frame you're in. That means that both the hyperbola and the light lines are invariant. The invariant is something that does not change across different reference frames. For the next portion of this video, we're making the assumption that you already know what time dilation and length contraction are. If not, here's a quick reminder on time dilation. It is the idea that objects moving at different velocities experience different amounts of elapsed time. Time moves slower for objects that are pushed faster. If this is new to you, it is worth pausing here before you continue. Okay, so let's now plot the invariant hyperbolas, which show all events that are in the same spacetime unit. Two types of invariant hyperbolas, ones that open along time, known as time-like, and ones on space, known as space-like hyperbolas. Every event sitting on one of these curves shares the same invariant spacetime interval, no matter what frame you're viewing it from. Each of these points is experiencing its own absolute time. Absolute time is the time experienced by an object being measured in its own reference frame. For example, if a rocket is moving really fast and only 2 seconds have elapsed for the rocket itself, whereas for us it might have been a couple of minutes, the rocket's absolute time is only 2 seconds. Every point along a single time-like hyperbola represents one identical amount of an object's own elapsed time, no matter how fast the object is moving relative to anyone else. The world lines that are closer to the light lines are experiencing a time much slower than the others. It shows the idea of time dilation, as an object approaching the speed of light experiences time a little slower than the others. Picture an object moving at a percentage of speed of light from the point of view of an observer at rest. The object might appear to take 1.25 units of time to reach a certain point, but for the moving object itself, as it still lies on the time hyperbola, it has only been 1 second. This is because it lies on the invariant hyperbola. We usually draw our grids with straight horizontal and vertical lines, but in spacetime diagram, we could use hyperbolas instead to give a more accurate representation of absolute time from different time frames. That's all we're going to cover in this video. Thank you for watching.